I'm Daisy. I'm chairing this session on computational statistics. Our first speaker is Ibrahim Judah. I believe he is in Hobart, and he'll be presenting on adaptive regularized feature selection for high dimensional data.
I click on it, yeah. So if I click it, okay, hello everyone. So my name is Ibrahim Judah, and I am a PhD candidate at Macquarie University under the supervision of Professor Samuel Muller and Dr. Hoying Zhu. And what I will be presenting today is my work on adaptive regularized feature screening for high dimensional data, which was actually submitted for archive under the same title. Okay, so this doesn't work from here. Using these, okay. Okay, so modern data has some problems. For example, they could be very large, like the number of features could be in the thousands or even more than that. And also, we could have a situation where the number of features greatly exceeds the sample size as well. In addition to that, we can have highly correlated features as well. And for example, you can take this as an example. This is a data set that is collecting the genetic information from cells infected with prostate cancers in different stages. And what we can see is that you only have 92 cells, like only sample size of 92, but the number of features is 1,288. If you want to make a feature selection using such a data set, it will be very challenging. One of the solutions is called feature screening. And the objective for feature screening is to simply efficiently screen out irrelevant features while retaining the important ones. And for example, let's take this as an example. It's a similar data set where we have n is 92 and p is 1,288. What we do is we first rank the features, usually by their relationship with the response. So we measure the relationship between the features and the response, and we rank them based on that. And then after that, we order the features based on this ranking. And finally, we set a threshold. In this case, we set the threshold of 4. So we screen the features that are below 4, that are ranked 4 or less. Obviously, in real life, it will be more than 4. It's just an illustration, of course. Now, one of the existing methods that apply this approach is the Ridge-Holb method. And it's very useful because it has regularization. So it works better for correlated data as well. It stands for Ridge High Dimensional Ordinary Least Squares Regression. And it works as follows. So first, you fit a regression model, a full regression model on the full data set, all the features versus the response, to estimate the coefficient vector beta. And then after that, you rank the features by the absolute value of your estimated regression coefficient beta hat. And then screen the top k features, whatever k is, it's up to you. Now, when it comes to the fitting itself, you have two methods that you can use. The basic method, the one we know, is the Ridge-All-S. That's the ordinary least square method. But the problem is it heavily depends on p. The computational complexity of it heavily depends on p. So there is a trick that you can do. We get the same value using the Ridge-Holb formula, where instead of using the x transpose x, you're going to use the x transpose, which reduces the complexity and makes it with respect to n. So it should now be much faster when p is greater than n. But obviously, the OLS would be faster when n is greater than p. To illustrate this, we have here a simple simulation to demonstrate this. In the left, we're basically comparing the log of the execution time between the Ridge-Holb and the Ridge-All-S. On the left, we fix n to be 250, and we increase the p from 250 to 6,500. On the right, it's the opposite. We fix the p and increase the n. And what we can see here clearly is that the Ridge-Holb is faster when p is greater than or equal to n, but slower in the other way around. But our focus is actually on the p greater than n, so the Ridge-Holb is better for us in this case. Now, another thing that we need to consider is that in the Ridge-Holb paper where they introduced the idea of using Ridge-Holb for screening, they just suggested using a penalty r is equal to 10. And the issue with this is going to be illustrated now. So what we're going to do is we're going to basically do a simulation setting, a simulation study for two settings. The goal is to see what happens to the performance, or to compare the performance of different values for R. In this case, R equal to 10, 50, 200, 600, and in different settings. So we vary the correlation to see if the correlation has like a significant effect, or if it's something happens only for highly correlated data. And we measure what we call the sure screening probability, which is the probability of including or of retaining all the true features after doing the feature screening step. So we apply feature screening. Whatever we screened, we check if we have included all the true features. If we did, that's one case. We calculate the probability of this happening. And what we can see here is we have two different settings. And we notice that on the left, we have the low penalties performing really well, and the high penalties performing badly, and the opposite on the right settings. So in two different settings, we see a different result. This illustrates that there is no such thing as a one-size-fits-all penalty. You can't have this. You have to have some form of adaptivity in order to perform really well in all cases. And that is where we come into the picture, and we propose the adaptive iterative regularization. But before we go to that, let me tell you what are the limitations of what existed approaches for like estimation or for choosing an adaptive penalty. So there are some methods that are based on sampling, like, for example, bootstrapping, cross-validation. The problem with these approaches is that you have to apply the ridge formula multiple times, and for multiple samples, and also for different values for R, because you have a grid of different values for R as well. So it takes a long time, so many times you have to do it, which is not suitable in this case. The other methods that are non-sampling, they either rely on computing X transpose X, which again, as we said, it's much longer, or they are designed for N greater than P, which is not our case in this case. But this is why we come up with our method. In our method, the goal is, as you can see in the left side, to minimize the prediction error. The prediction error is the formula that you see on the left side, which is equivalent to the formula that you see on the right side. Now, the problem that you can see in the right side, what we call here the beta 0 here, this beta 0 means the true coefficients. So for non-true features, they will be zeros. For true features, they will be the actual true relationship between these features and the response. But this is something we don't know. So beta 0 is unknown. So we need to estimate it. The problem, though, if we want to estimate this, we have to do some form of iterative estimation, which is the idea of using iterative regularization. But if we do this, then we have to apply Ridge-Holb multiple times. However, we actually don't need to, because we can use the Ridge-Holb eigendecomposition. We can decompose the XX transpose matrix using eigendecomposition and make it possible to store the difficult computation one time, and then the fast computation can be repeated as many times as you want. So using this strategy, we use the following algorithm. First, we apply Ridge-Holb screening with initial penalty R0. Then we use, after the screening, we screen such that we have the number of features less than n. Now it's possible to fit an OLS model. When p is greater than, you cannot do an OLS model, but when it's less, it's possible. So you estimate beta in this case. And after estimating the beta, now you can update the initial R. Now you can actually do the optimization. You can actually find the optimal R using Newton method, very simple. And then after that, you reiterate, change the R0 into the R hat that you update, and continuously iterate until you converge. That's basically the idea of the iterative method. So first, let's see what happens to the speed. As we said, we're using eigendecomposition. Isn't it really working? Yes, it is. So what we see here is two plots. On the left is the same plot as we saw before. I just added the Ridge-Holb. And from the left, we can see that it's the same complexity as the Ridge-Holb, because it follows the same function, so it's basically the same complexity. But it's longer. How much longer? You can see that from the right side, where you see the execution time, it's about twice as long. So it only takes twice as long, not like 100 times or 1,000 times longer, which is good. The next thing is to see, is it really adaptive? OK. It is indeed adaptive, because we can see now the green line is the Ridge-Holb is performing well in both cases, the one on the left and also on the one on the right. So it is actually performing well. Then I wanted to see when exactly does the air hole performs much better. So I did a comparison for all the value for multiple values for n and p, and computed the probabilities for both the air hole on the left, the ridge hole with a penalty of 10 on the middle, and on the right is the difference. And what we can see that yes, air hole is generally outperforming, but most of the increase in the performance is when n is close to p. Finally, here we just did a simple comparison, but remember that previously we used a threshold, but we fixed the threshold. Now, what if we use a different threshold? This is what we're trying to do here. We're trying to see when exactly are we satisfying the sure screening property, or when we exactly are retaining all the true features. So when it's less, it's better. And we can see that for any value you choose for the threshold, you're still performing better using the air hole versus the ridge hole in both of these settings. And that's basically it. Thank you very much.
Thanks very much, Ibrahim. Our next speaker is Jason James Lamb, who is presenting online, and they will be talking about sequential Monte Carlo for the discretely observed multivariate Hawkes process with an application to terraced activity modeling. Are you there, Jason?
Yep. Can you guys see my slides?
Excellent. Take it away.
Awesome. Right now, everyone. Yeah, my name is Jason Lamb, and I'm a PhD student at UNSW Sydney, and I'll talk a bit about the use of sequential Monte Carlo for point processes with incomplete data. There we go. So I'll start with an intro to the core problem and then give a brief description of the methodology I've been working on, and finish with an assessment of the method and an application. So when you think of a point process, what we have is a random evolution of events that are popping up over time. And in a multivariate setting, those events can be of different types. Now, when we conduct likelihood-based inference, ideally we would like to be able to see exactly when each of those events occurs, but often due to maybe some cost factors or imprecise measurements, we only have access to this lower figure, which is the number of events in these disjoint time windows. So you could think, for example, of weekly COVID case data, something like that. And this can make inference quite challenging. So we focus on the multivariate Hawkes process. Formally, we've got this sequence of random event times denoted by tau. And with each time is paired a type. So an example relating to the application later, you might think of an event being a terror attack and its type being a location marker, like what country it occurred in. And the events are driven by an intensity process. This is like the instantaneous rate at which events are popping up, and it has a few components. So we can see here in blue, you've got the intensity of type 1 events, and in orange of type 2 events, and they sum up to give that total intensity. Underpinning it is a background rate. That's like the baseline minimum rate at which events can be arriving. Now, when an event occurs, say an attack in country A occurs, the model allows for that to spike the intensity in country A and make other events more likely for a short time, but it might also cross over into country B and excite events there as well. So the size of that triggering effect is quantified by these jumps, or branching ratios we call them, labeled as eta. And once that spike occurs, the effect will decay over time based on the shape of a density that you pick. So in this case, I've used an exponential, and that's characterized by offspring parameters. So these are the different parameters of the process that we're interested in. So we get a bit ugly on this slide with the notation, but we've got a counting process for each dimension. It's just the number of events that have occurred to a certain time, with the counting process of all events being the sum over the dimensions. The problem we're facing is that when you can only observe the process on these disjoint windows, the likelihood function is this expression here. It's this probability of having observed those counts, but no closed form expression in terms of the parameters available. So we can no longer do maximum likelihood estimation on the process. So we need to think of some other ways to do it. These are some notation we refer to. The main one is just this one at the bottom. P of theta is the distribution of those observations. So we're going to use sequential Monte Carlo to estimate that likelihood function. It starts off with a state space representation of the problem. We think about the observed values being those counts that we see, and the hidden variable being these unobserved times and types of each event. What we can do is we can write this likelihood function as a product of conditional probabilities relating to each increment. These are one here. And each of those can be written as an integral with respect to a filtering distribution. So the goal of sequential Monte Carlo is to, rather than simulate an entire sample path and try and calculate a probability, which takes a lot of computational power, to take a small sample on the first increment and evolve it at each step to each subsequent increment and at each stage, getting an estimate of these likelihood factors. So we'll take a look at how we achieve that. Suppose we've done all the hard work and we're at time I minus 1. So what I've got is a sample of J particles, and they're distributed according to this filtering distribution. It's the distribution of the unobserved variables given the observations. And what we can do is write down the filtering distribution in the current time step as proportional to a product of this likelihood factor out the front, which is easy to evaluate, and the filtering distribution at the previous time step. So we can see a link between the previous step and the current step. We want to evolve our set of particles to be a sample from the current time step. So what we do is we start off by resampling our particles from our estimated distribution. This just allows the computer to kind of focus on the regions that are most important. We then propose new event times. This is like importance sampling, a typical importance sampling. We actually just use the ordered uniform distribution to do this and then randomly allocate types. So it's a really simple proposal, but it seems to work quite well. Once we've got those, we weight them, just like normal importance sampling. And we end up with a weighted sample that is from the filtering distribution at the current time step, which is what we wanted. And we can then, with our sample, estimate the normalizing constant, which is that likelihood factor that we wanted originally. And maybe surprisingly, when we take the product of all of our likelihood factors, we actually get an unbiased estimate of the likelihood function. Now, this is done for one specific choice of theta, of parameter. To get from this to an actual estimate of the true parameter, we make this observation that, as is typical with sufficiently smooth and regular parametric models, that the likelihood function should be approximately proportional to the density of a normal distribution centered around the MLE. So if we plug our unbiased estimate into an otherwise typical Metropolis-Hastings MCMC sampler, we should at the end up with a sample that's normally distributed around the MLE, and then we take our estimate to be the mean of that sample. So this is called pseudo-marginal Metropolis-Hastings, and it's justified that the marginal of that resulting chain is the true likelihood. So ideally, we should end up with some unbiased estimates, and we'll see if we do now. So here in blue, we've got our estimates. This is on 500 different sample paths simulated from a set of parameters denoted in red in the figure. We simulated that for 200 time units each and aggregated to widths of 0.1. This is a very low level of aggregation for this particular example. We can see that we've got pretty low empirical bias, as we were hoping for. And that bias only increases mildly when we increase the aggregation level. And in yellow, we've got a competitor method at the moment, which is sort of a modified version of Monte Carlo expectation maximization, proposed by Shlomovich et al. In 2022. And we can see with their method, it's incurring some pretty significant bias. So at least at the moment, it seems that our method's performing quite well, though it is more computationally expensive. So for a quick application, since everyone might remember, the United States conducted a full military withdrawal of Afghanistan from March 9th, 2020 to August 30th, 2021. And since then, there's been some fairly significant media attention in Pakistan as to whether this has contributed to an increase in terrorism in Pakistan flowing out of Afghanistan. So the latest data available from the Global Terrorism Database was daily count data from March 9th, 2020 to June 30th, 2021. So we wanted to test whether we could detect any cross-excitation between the two nations over this period. So we see in Afghanistan some pretty significant clustering and quite high level of aggregation, with some less so, but still quite significant aggregation in Pakistan. So with Afghanistan denoting a type 1 event and Pakistan a type 2 event, we just use a simple model, so constant baselines and exponential offspring densities. If I draw your attention to two of the estimates here in red, we've got eta 1, 1. So this is the self-excitation parameter in Afghanistan. It's saying how likely is an event in Afghanistan to trigger other events within the country. And that's very high. So it's saying that there's quite a significant short-term risk of an event in Afghanistan triggering follow-on events. But when we look at ETA 2.1, that's the effect of an event in Afghanistan crossing over into Pakistan. That came out very close to zero. So this is saying that at least according to a short-term clustering mechanism, it's unlikely that events in Afghanistan were, at least during the US exit, triggering events in Pakistan. Now, that may have changed since, and there may be other structural links between the two countries, but at least here we weren't able to detect that sort of short-term clustering interaction between the two countries. And here we've just got a plot of the true data in red compared to 500 simulated sample paths from our MLE estimate, just to check that our model isn't significantly disagreeing with the underlying data. And so everything looks pretty okay there. Awesome. Well, thanks
1 minute to go.
Yeah, thanks for listening, and yeah, I hope to take your questions in the Q&A.
Thanks very much. Great talk, thank you. Our next talk is from John Collins, who'll be talking about evaluating the cross-panel transferability of machine learning models for predicting panel non-response. And John will be joining us online. John, are you there?
G'day there. Can you hear me okay?
Excellent. Thanks, John. Take it away.
Brilliant. Here we go. Let me just start up the slideshow. Okie doke. G'day there, everybody. I'm coming to you from a sunny Mannheim morning. So this is evaluating the cross-panel generalizability of machine learning models for predicting panel non-response. So my name is Jack Collins. I'm a PhD student at the University of Mannheim, and this research is being conducted along with my supervisor, Professor Christoph Kern from the LMU in Munich. So the problem that we are addressing in this research is unit non-response in longitudinal survey. So you've got your panel of survey respondents. You've got 1,000 panelists, 5,000 panelists. Every 3 months, every year, you're going to ask them to fill out your survey for you, and every time some percentage of them fail to do so. And this puts holes in our nice, neat timeline of what is happening with a given individual over time, which is what we want from our longitudinal survey. Now, past studies, and we're going to go over them in a minute, have shown that machine learning can be used to predict, with a given level of efficacy, each panelist's probability of non-responding in the future. So we can attain a certain level of predictive accuracy with machine learning when we're trying to predict who's going to non-respond. Something that we're going to talk about later is that with this machine learning approach, though, we have to wait until you've completed at least 2 waves of your panel. And if you've got an annual panel, that's 2 years. You have to wait until you've got one survey wave completed for your training data and another survey wave completed for your test data. And only then can you start to make real predictions going forwards. So that brings us to the research questions for today. What we are going to talk about is, so we have these prior studies that show us that certain machine learning approaches were effective in certain panels. So that's fine, but if I've got a panel and I want to know what propensity model is right for me, I want to know whether an approach that I see in a given paper is going to generalize to my panel. And so we're going to see how well do these approaches work when they're applied to lots of different panels. And if they work very consistently, then that's good. That means that when we start up a new panel, we've got a decent amount of confidence that the same approach is going to work well for us. But if there is an approach that works consistently well across different kinds of panels, that opens up another opportunity, which is that we could pre-train a model. That means that we could train a machine learning model on one panel survey and then use it to predict people in another panel survey. And this way we could have our model trained and ready to go before day 1 and ready to make predictions right away instead of needing to wait for 2 waves to complete first. And that's especially important because in a lot of panel surveys, you get the most attrition of panelists in those early waves. So let's talk about some of these prior studies. So there are lots and lots of studies out there where people fit models, make predictions, and publish the results. We've just got a handful here. And what I'm going to tell you is about this number, area under receiver operator curve, OROC. That's a number that goes from 0.1, which means it was a perfect classifier, perfectly guessed everybody, to 0.5, which is the worst possible classifier. Across these different studies, what's happening here is that they're taking a single panel and they're trying a lot of different models and they're publishing the results. So that's fine, but we don't know whether these approaches work across different panels. What's the predictive accuracy of these models? In words, we can put it as follows. Of those who non-respond in a given wave, we can predict about half of them correctly, but of the guesses that we make, about 20% of our guesses were wrong. So that's the predictive accuracy of these models, but we don't know whether they work well across panels. So to test that, we are going to take 5 different longitudinal surveys, all of them with various differences between their designs. Some of them are annual, some of them are weekly, some of them are online, some of them have a post component. We're going to take all 5 of these different panels, and we're going to train equivalent machine learning models across all of them, and then we're going to see whether there's any big differences in what machine learning algorithm does better in different circumstances. So let's talk a little bit about that modeling approach. So we're going to start with our 5 panel surveys. Then we're going to derive an equivalent set of machine learning information across them. So we've got our predictors. The things that we're using to predict non-response are demographics, age, income, etc. Non-response history. So for every given participant, that is the proportion of previous waves to which they were invited but did not respond. And then we have the count of invited waves, the number of waves they've been invited to in the past, and that's to account for survey fatigue. And we're going to fit these machine learning algorithms to predict this dependent variable, which is a binary variable, and it's just, will this participant non-respond in the next wave that we invite them to? Yes, no. So that's our predictors, that's our dependent. What are the algorithms? And we're not going to go into the details of how different machine learning algorithms work today, but we're going to pick a set of models that were common in the preceding literature, and that's penalized, unpenalized logistic regression, and it's some tree-based models, random forest, and gradient boosted classifier. And then we're going to evaluate how good were our predictions. How good were the predictions that come out of these models in terms of not generating too many false positives, not too many false negatives. So 5 panels, 4 different kinds of models. How did they do? So we got 4 panels here. There's a 5th panel out there, but that 5th panel only had 3 waves at the time that we did this. And as I said before, you need 2 waves to train your model. So we could only do 1 prediction for that 5th panel. We'll talk about that in a second. But you can see that across all of these panels for which we have many waves to see how accuracy of these propensity models goes over time, you can see that after a certain starting level, we converge to an overall long-term average. And that average tends to be something between 0.8 and 0.9 out of 1.0. And so that's pretty close to the predictive accuracy that we talked about earlier. And it was the same for the Frida panel that got an OROC score of 0.8. Okay, so these different approaches. And by the way, it doesn't look like the particular choice of model matters that much. Overall, random forest is the best one, but not by too much. So the choice of model doesn't seem to matter. These predictors seem to be pretty good, and they seem to be consistently pretty good across all of these different circumstances, except that there's a bit of variation in the first few waves. So that opens up this idea. Could we pre-train a model? Could we take a model that was trained on a previous survey and apply it to one that happened later? So let's take a look at what that would look like. This is the GESIS panel. And this is simulating us taking data from the German Internet panel that started earlier, a year earlier, And we're going to take the data from the German Internet panel, we're going to train our model, and it's going to be good and ready to go before the GESIS panel even starts. The first thing that's going to happen is we're going to try to predict the very first wave of the GESIS panel, and it's going to go terribly. That's 0.6 OROC out of where 0.5 is the worst, so pretty lousy performance in the first wave. And why? Well, that's because non-response history is a really important predictor. And in the first wave, there is no non-response history to exploit, so we don't do very well. But from the second wave onwards, suddenly we do very well, a lot because we have some non-response history now to work with. And in fact, this pre-trained model here was better than if we could have even retrospectively made predictions with a model trained on GESIS panel data. And we see this pattern consistently across applications. So any time that we have a pairing of models where one came before the other, so we can do pre-training across our 5 panels, we did this. We consistently found that the first wave wasn't very successful, but the second wave, which couldn't have been done as early otherwise without pre-training, was very successful. In fact, in the case of the Frida panel, a totally new survey, that had only just accomplished 3 waves. In the second wave, we did significantly better than if we had been working without pre-training and even just making these retrospective predictions. So the takeaway here is that pre-training is possible. It tends to be most effective from the second wave onwards, and from that third wave onwards, you've now got data from your own panel that you could make your own train your own model. So perhaps you don't need pre-training. Although we did find that the pre-training models worked pretty much as well as models trained on that panel's own data. So this indicates that there's a lot of ubiquity among what is good at predicting non-response, a lot of ubiquity in what algorithms are good. And I think that's my 10 minutes there. And so we are done. Thank you very much for listening, and I'll hand it over to Daisy.
Thank you so much. That was such an interesting talk. We have one last presenter in this session, and that is Connor Maurice John Stewart Green. Connor's here in Perth, and they'll be presenting on maintenance optimization for latent degradation systems.
Here we go, and is it just arrows in space? Cool. All right. Hello, everyone. My name is Connor Stewart Green. I have just finished my master's thesis, and I am presenting the results to you all today. That being maintenance optimization for latent degradation systems. Oh, you all right? Cool. Before we begin, I'd like to take a quick moment to thank my supervisors who have been a great support throughout my research and the general thesis writing process. So, to begin with, I would like to give a quick overview of what degradation is as a general concept. I'm sure everyone is aware of what it is, but it's good to get a baseline understanding. Generally, it is described as the process by which a system or component degrades to a point where it's no longer able to fulfill its intended function, in which it usually comes under either a biological or an industrial context. Our research was interested in industrial contexts, so all of our data was monotonic by nature. However, our research can apply to some biological systems, such as cancer. For an understanding of what can go wrong with degradation, here is a rather personal picture. This picture was taken 3 years ago at the site of an accident that my dad was unfortunately in. Before anyone asks, he's fine, he made a full recovery, but he very easily could have died in this accident. Hence my personal interest and stakes in this research topic. So, needless to say, with events like this occurring, people have a distinct interest in preventing it through the use of maintenance and maintenance policy. Of these, one of the more popular ones is condition-based maintenance, which is often preferred due to relying on the directly observable condition of the system, making it both cost-effective and practical for many applications and many industries. However, by the name, its major weakness is that it relies on observable data exclusively. And I'm sure anyone who's had a shelf collapse out of nowhere would understand that not every breakdown can be directly observed ahead of time. In these systems, time-based maintenance might be preferred. However, what if we could measure this type of degradation that we can't directly observe? This type of degradation remains latent within the system and is what we refer to as latent degradation. While it is characterized by our inability to directly observe this type of degradation, so it can be things like cancer, subsystems within a very tightly compacted machine, or it could simply just be the added up corrosion over time. Past studies, specifically the one by my primary supervisor, have managed to successfully have successfully been able to estimate latent degradation through the use of performance characteristics which are correlated with the current true degradation state. This process is referred to as the marker process, and in order to estimate, there we go, whoops, to estimate the overall effect, they used a bivariate gamma process, specifically Kibble's bivariate gamma distribution, the PDF is there, where x of t is our latent degradation state and y of t is our marker process. Bearing in mind that we can only make decisions based on our marker process, where the only thing the x of t can reliably contribute is a breakdown. We assume, of course, those are self-announcing. My research was to expand on these past studies by implementing repair mechanisms, as they were only interested in systems that only replace the system. And wouldn't you know what I found out? So in my research on past studies on what imperfect repairs have occurred for the bivariate gamma system, I found out there was pretty much nothing. So to keep it simplistic, we used a uniform distribution, all of the details are up there, to estimate the effect of imperfect repair at the time of a repair. Therefore, we were able to construct our policies, to which we were interested in two primary ones. One, where all of our decisions were based directly on the marker process, and another one where we leveraged the correlation between our marker and our degradation to make our decisions. We considered 3 decision variables, with the third one only applying to the second one, which here's an example of what an individual plot looks like, where the red line denotes our latent degradation state, the blue line denotes our marker process, or the observed state, and the blue region is the area that we expect we want to do an imperfect repair. At times T1 and T2, an imperfect repair occurs, and at T3, a perfect repair occurs. And this is the underpinning sort of process that we use throughout all of our analysis. So, for our first policy, referred to as the classical maintenance policy, we found that as the correlation between our two processes increased, the long-run cost, which is the cost divided by the lifespan of the system, decreased as it became more correlated. The preventive threshold, as for the decision variables, the preventive threshold had a maximum at around 0.5, decreasing for variables lower than that and remaining roughly constant for any systems more correlated. And likewise, the inspection interval was sort of all over the place. For our second policy, the intelligent maintenance policy, we can see that our long-run costs are lower compared to the first policy, implying that it's better suited for producing lower costs, likely due to preventing the worst-case scenario breakdowns. Our tolerance policy has a local minimum at about 0.5, increasing for correlations that are higher and lower. Our preventive threshold has a similar trend, though it's not quite as consistent, and the inspection interval increases as the system becomes more highly correlated. We also, so both of these were in respect to systems where our scale parameter for both the latent degradation state and the marker process were equal, but that's not necessarily true for every system. So we performed some sensitivity analysis. First, considering when the scale of the degradation state was higher than the scale for the marker process, this correlates to a higher likelihood of false positives occurring. Hence, our long-run cost for both systems is decreased because the system tends to live for longer. We also tested the opposite extreme, where likewise the long-run cost of the system increased. Here are the results for specifically the long-run cost, which is the actionable part that we prioritized for our primary scenario as well as the sensitivity analysis. We can see that universally our second policy is able to produce better estimates, i.e. lower costs, and the highest estimates occurred for when correlation was incredibly low, and the scale of our latent degradation system was less than that of the marker process, and vice versa for lower costs. With that, this is more or less the end of my presentation. How do I do time-wise? Sweet. Yep, here are some references. I would recommend checking out the topmost one, since that's the study that this study was originally based on, as it has a lot of the underlying mathematical principles involved. There's a lot of them, so for brevity's sake, I skipped them. But thank you.